Welcome everybody to OpenCV Live, and today we are going to present you with a tutorial for document scanner. And we had a similar tutorial a couple of weeks back where we showed you how to create a document scanner from using traditional computer vision methods, right? The idea was that you take a picture of a page lying on the floor or on any flat surface, and the idea is that you take a picture of that and we align the document horizontally and vertically so that it's nicely, perfectly aligned. And we showed you one technique on how to do it and how it was done traditionally using traditional computer vision techniques. Today, we are going to improve upon that and show you how to do it in a deep learning, one specific part of that, how to do it using deep learning, right? So before we go there, I want to introduce you to Phil Nelson, who is the Director of Content and Creative at OpenCV. He organizes the show, and if anything goes wrong, it's his fault. Before Phil, I'll let you, introduce yourself. But I also want to introduce Vikas Gupta, who is the Director of Courses at OpenCV University. So Vikas, why don't you go first, and then Phil will do his. He has a lot to speak.
My spiel.
Right.
Welcome, Vikas.
Yeah, hi everyone. I'm joining from India in Bangalore, and I have been associated with OpenCV for about 5 years now. And it has been more than 5 years, and we have been creating amazing content and amazing courses on computer vision and deep learning. And I hope, and I know some of you guys, I can see Theodora is here, and I can see many more people who are joining who are our students. And I hope that you will really like this webinar. So welcome all of you.
All right.
Yes, and it's me, PHILLIP. It's your co-host with the co-most, the second banana who is second to none. I'm also your plus one and only. It's Mr. Nelson. If you're nasty, but you, my dear friends, can call me Phil here on OpenCV Live, and I'm here to remind you of a few things that we do on every single episode of this show, the first of which is a giveaway to you in the audience. Stay tuned. Later on in the episode, I will be asking a trivia question based on the presentation from our illustrious host, Dr. Satya Mallick, and the very first person to answer that question correctly in the Zoom chat will win the OpenCV course of their choosing, absolutely free. You can see what courses are on offer by going to opencv.org/university. We're also taking questions from you in the audience all during the show. Use the Zoom Q&A button if you're in Zoom or the chat system wherever you are watching us. We are live damn near everywhere on Al Gore's internet, so please talk to us there and we'll do our best to answer questions on the air. If we don't get to your question during the show, please send your questions to newsletter@opencv.org and we'll do our best to answer them there. Before we get started today, I wanted to talk about one quick thing. OpenCV launched a pretty dang cool new thing this week in beta. Satya, do you want to talk a little bit about the OpenCV computer vision job board? I'll share the screen here so you can talk over it.
Yeah, so we have this, we keep trying to figure out ways of helping people start a career in AI, right? OpenCV University's goal, right, our mission is to train the global workforce in AI, right? And when we train the global workforce, we also want to make sure that it's not like, okay, they are learning specific techniques, etc. We want to make sure that we are training people for an AI career, right? And because of that goal, we keep adding new things that people would be, would get benefit from. So this it's a very simple job board, right? jobs.opencv.org. You can go here and check out various listings of various jobs, right? And it is completely free to use. We decided to open it to all the users. Initially, we had thought that, okay, this would be for OpenCV University students only, but then we decided, okay, we are going to just open it for everybody, right? You don't even have to log in or anything like that, right? And you can go and it's a very simple interface, right? You basically go and do a search based on your country and some skills you may have. Let's say you want to do, CNN, or you want to do, and you want to look for a remote job. So country, remote jobs, and the skills. And you get a list of jobs that are published at various places, including LinkedIn and a few other job sites. You click on it, you can apply there, right? So as simple as that. We would love to have feedback for the site, right? We don't want to make it overly complicated. We want to keep it simple, but I do want feedback from you. What are the things you like? What are the things you don't like? What are the features that would be more useful? But this, the vision is that this would be the place where all computer vision jobs reside, so that you don't have to go to different places and try to figure out, for each place, put in the right keywords, etc. These are the places, where all the computer vision and AI jobs are listed, right? So easy way for you to just go and check out all the jobs. Yeah, that's jobs.
So go check out that's right, jobs.opencv.org. Check out the beta here. I think this is only the second place we've talked about this, that we posted on LinkedIn a couple days ago, and people are getting the inside scoop here on OpenCV Live. Before we get started, quick reminder, OpenCV has merch. You can go to opencv.myspreadshop.com. Free standard shipping for the next 6 days. So you can pick up one of these sweet I Love OpenCV shirts in English, simplified Chinese, or in Espanol. We've also got buttons, pins, patches. I've got some of the buttons here. I'll start my screen share to show you. I've got one of the little I Love OpenCV buttons here. Go pick those up. I'm wearing the shirt. What more do you people want from me? Go to opencv.myspreadshop.com. Free standard shipping today. And please support OpenCV in any other way you can. We've got OpenCV GitHub sponsors, and you can donate and support to OpenCV at opencv.org/support. Thank you so much to everyone who has. Even small amounts of money really mean a lot to us because it shows us that you care. Satya, back to you.
All right, one last announcement before I start the presentation. We are working on two things, right? And both have a non-zero chance of not happening, but I just want to announce it regardless. I cannot give much detail. One is OpenCV conference that is it will probably happen in May of next year in San Jose. We will give you the details as this thing solidifies. The next one is OpenCV competition, and there are some big names who we are trying to get.
People have been asking a lot about the competition this time of year because they're like, hey, why am I not participating in a competition?
Right. So this will happen hopefully by mid-November or end of November, we will be able to announce it. But things are looking good there. It's going to be a very technical competition.
A little bit different than the previous competitions, I think. A little more. I think it'll be exciting. It'll be great to see what people do.
Yeah. All right. So let's get started. And if you have any questions, you can ask in the chat section. Even though I may not be able to answer directly, Vikas will try to answer as many questions as possible, and then we will have a Q&A session in the end, and that's where you can ask the questions as well. But and Vikas is also going to share the tutorial notebook with this, right? So
one more quick note here. People keep asking. The recording of this episode will be available on the official OpenCV YouTube channel, youtube.com/OpenCV official.
Right. All right. So let me share screen. Are you able to see my entire screen?
Yes, indeedly do.
Okay. So that's great. It's not showing the green thing it usually shows, but okay. It says
the
University,
Zoom
right?
thing? Yeah, I can see the whole thing, yes.
All right, that's great. Okay, so
looks good.
All right. So in the previous, on September 2nd, I think, we had this automatic document scanner where we gave you a computer vision method of solving this problem. The problem is that you have a document or a sheet of paper which is laid out on a flat surface, and you take a picture of it, but now you want to rectify it. You want to make sure that, okay, it's aligned, axis aligned, right? And then, the process we explained was very simple. First of all, we did some morphological operations so that the inside of the image became white, right? And this was, This was to improve the quality of segmentation. And then we did grab cut so that, from this image, we went to this mask kind of image. And then we used edge detection and contour detection. And finally, we did, on that contour, we said that, okay, simplify this contour. This contour should actually be a rectangle and give me the 4 points. You get the 4 points. And from there, we were able to apply a homography to it, which rectified the image, right? So this is, this is pretty standard process. There are some challenges in this process, though, right? The very thing is that, okay, grab cut, because grab cut is not based on machine learning, right? It is based on building a model for color, right? So in grab cut, when you look at this, suppose we want to segment this document, you provide 3 regions. The first region is inside. You have to have the pixels which are definitely document, pixels that are definitely background, and pixels which are in the, we don't know whether it's background. So the unknowns, and those are the 3 regions we need to specify. Sometimes that region is basically specified using a rectangle, and that works fine too, right? However, GrabCut doesn't understand, it's not based on machine learning in the sense that the single document, you don't train GrabCut to produce a result. You just use GrabCut off the shelf. It works fine for many, many applications, but you don't need to train, right? It builds a model, a color model, based on the pixel values in the image itself, right? So you didn't use other images to train the model and produce this result, right? It uses pixel values. It has some heuristics inside it that enables it to figure out, okay, this is the background, this is the foreground, because it builds a color model based on what is the background, what is the foreground. You already said these pixels are definitely foreground, and then you said these pixels are definitely background. So it has the capability of building a color model and then using a graph cut algorithm to segment out the image, right? And these kinds of techniques are great when you do not have data, and they work out of the box on many applications. Let's say you want to do some industrial application where the lighting is very constant, things are regulated. You may be able to get away with something like a grab cut. But when you are actually sending these kinds of applications to a user, right? It's a untrained user on the internet. In that case, a solution based on GrabCut may not work to the precise level of satisfaction, right? So let's say in these cases, right, you can see that the background is very close to the foreground, and GrabCut may not do a very good job because it is based on understanding the color distribution. When there is a difference between the background and the foreground, the color distribution, then it does a very good job. But when things are very similar, you can see that it's white paper on white background, then it's not going to do a great job. It may also not do a good job when you have, when the entire image doesn't contain, the document is not contained in the image, right? There are these obstructions, occlusions, etc. But we can train a segmentation model that will be able to do this, okay? So basically, we use an image segmentation model. And again, why do you use deep learning? Because you can generalize. So one thing with GrabCut is that if it fails, right, you have you can do very little to make it work, right? If it fails, you're pretty much done. You may change the bounding box. You may change a few things, but there is not much. You're stuck at that level of accuracy. In case of machine learning, right, this is why machine learning is so powerful, and deep learning in particular is so powerful, is let's say something fails. All you do is take similar examples, right, put it in the data set, and suddenly that class of problems gets solved, right? You may have some other problem, and again, the procedure is the same, right? You find all the problematic cases and then put it in the training set. and it starts working for that class of problems, right? So that is why learning-based approaches are so useful. You don't need to be an expert to use them. All you know is, okay, it fails in these cases. I'm going to collect some data that looks like this, put it in the training set, and it will magically start working, okay? So example of, this kind of example would not have been very easy to fix when we are using traditional computer vision methods. But with deep learning based methods, we are able to solve it pretty reasonable. This result looks pretty reasonable. Okay, so here are the steps that we will take to create a robust document scanner model. First of all, these whenever we train a deep learning model, they are very hungry. They want a lot of data, right? So we want to make sure that whatever data we start with, we are maximizing the usage of that, right? We are using we are trying to create synthetic data from existing data as much as possible, right? And then we will apply some pre-processing. We will do some data augmentation. And we will then show you how to load different deep learning architectures. There are, basically, we are going to use something called Deep Lab V3. This is a segmentation model. And inside this model, there are a few options for, there is an overall architecture, but there is something called a backbone, right? Which means that, okay, how big of a model this can be. And we'll come to it. So we'll choose a deep learning architecture, and then we'll choose the appropriate loss function and evaluation metrics. Loss function basically is a function that encodes the error, right? How much error is your model making? And that error is used to update the model, right? And then evaluation metrics is basically the metrics that we run on the test set to show, okay, what is the accuracy of the model, okay? And then finally, we will train and evaluate the model. So, synthetic data, here's the pipeline for synthetic data generation. In our training set, we have images that contain the original image and the mask for the image, right? And let me show you what the training set looks like. Give me 1 second. Okay, are you guys able to see my
your Finder window? Yes.
Yeah, Finder window. Thank you. Right. So these are the images, right? And you can see that these images are not easy, right? These are pretty bad images, so to speak, right? These are the images, and then
they look like they're from a PlayStation game.
Right. I actually don't know where these images were collected
90s
from.
Texture video games.
Right.
N64 document scanner.
Right. And these are the masks, right? So these are the masks that correspond to those images. And we have a training set and we have a validation set, right? Training set is the part of data which is used for training the model. Validation set is the part of data where we are going to evaluate the model. So this data is never shown to the model for training. So otherwise it will memorize it, right? So that's the data we have, but we want to use more synthetic data, right? So when the idea to do it is that, okay, we start with this, there are these two things, right? The mask as well as the original image. And then we can create more data by synthetically creating this, we can produce many different backgrounds and combine them to produce this image. You can see here that the mask is used to combine the original image as well as the background. And now suddenly you can keep changing this background image, right? You can keep changing this background image and produce a lot of new images, right? What is not shown here, but you could also do is you could transform the original image. So you could take this original image, apply some image transformation. Let's say you can apply some homography to it, right? You can change the you can scale the image, you can rotate the image, you can apply a shear to the image, do the exact same thing to the mask, right? So you get another set of the same image, right? And then you apply a different background. So now suddenly, let's say you had a data set of 1,000 images, you can easily get to 10,000, 100,000, whatever you want, right? So that's one way of creating synthetic data, right? Okay, so here, after doing this kind of background changing, you can see that we can generate a whole bunch of new images. So we'll go over the code, but I just wanted to outline the process, and then we will go and look at the code. Now, when we, in this example, right, there are two things, right? One is the original image, and then we have the background mask, and we have the document mask, right? These two things are the ones that we need to generate given this image, right? And when we load our data set, basically we will load one of them, and the other background mask is just the inverse of that. Okay. Now, as I said, that we are going to use two different architectures. We will use DeepLab v3, which is a segmentation architecture, right? And in a segmentation problem, every pixel of the image needs to be assigned a label, right? In our case, the labels are very simple. One is the background, the other is the document, right? So there are just 0 and 1. It's a binary mask that we are looking at. But inside DeepLab v3, so think about DeepLab v3 as this large architecture, but there is inside it, think about a black box that does feature extraction. This is a combination of many different, these blocks. You can think about them as a lot of convolutional blocks, right? And if you don't understand what are convolutional blocks, don't worry too much about it. Just imagine that there are these blocks of parameters, right? So there are the greater the number of parameters, the more capable the model is, but it can also memorize a lot, which is not a good thing, right? This model, ResNet 50, it's a very popular model, right? It is a 42 million parameter model. It gives a better accuracy, right? We will go over what is mean intersection over union score, but it gives better accuracy, and it's
42
relatively
million,
fast. Yeah,
only 42 million parameters is basically a baby compared to now.
Yeah. I mean, now we keep hearing about these
78 billion.
Yeah, for foundation models, for these large language models, right? So, but when you're running some things on the edge, even 42 million is, it's quite substantial.
Definitely.
Yeah. The MobileNet v3 backbone, if we use the MobileNet v3 backbone, it has only 11 million parameters, right? It is fine if you want to run something on a mobile device. The accuracy may not be as good as the ResNet 50 backbone, but you will be able to do real-time image segmentation in many cases, even on a phone or a small device, right? So we'll give you a way to experiment with both, whatever works for you. Okay. Then I just want to go over what is a loss function and what are some evaluation metrics. And this loss function is specifically for for image segmentation. So now let's say you have two things right here. You have the ground truth, which is the mask. During the training process, right, we are giving it the input image and the mask. And during inference, when we actually have trained the model and we are ready to work with it, then we give it an input image and extract the mask. The mask is the output, right? While we are doing the training process, we basically, to train a model means to update the weights and biases of the model, right? And I'm just going to use the word weights to mean weights and biases, but think about it as a black box that has a few million knobs, right? 42 million knobs. And when the knobs are in the right setting, given an input image, it will give you the right mask, right? And if they are not in the right setting, then you will not get a good mask, okay? Now, ground truth basically means the input mask that we are supplying. That is the ground truth. That is the data that it is going to learn on. After you have trained it for a certain number of times, you will get a mask. It will not be accurate. Now you compare the two masks, right? And when you compare the two masks, you need to figure out, okay, whether it is whether it did better than the previous model you had or not, right? So the comparison is done using two different metrics. One is called, these are two different metrics which are popular for image segmentation. One of them is called the DICE score, right? And it basically looks at, the ground truth, the intersection of the ground truth with the prediction. This inverted U, if you remember from high school, it basically means intersection, right? So you basically look at the number of pixels which are intersecting between the ground truth and the predicted value, divided by the number of ground truth pixels plus the number of predicted pixels, right? So this is the DICE score. And of course, if you have perfect overlap, you can see here that if you have perfect score, then this intersection is going to be basically 100%, right? And these two numbers will basically cancel out. The DICE score would be 1, right? The other one is intersection over union, right? And you can see that they are kind of similar. You basically take the intersection over the intersection of the two masks divided by the union of the two masks, right? Now, which one is better, right? So DICE score is used when you need high precision. Let's say you are working in a medical domain where the masks are little, cells, right? They are very little, and you want to make sure that you get those cells. You cannot afford to miss those cells, right? In those cases, typically you would use a DICE score, right? And if you have, but in our case, right, intersection over union is a better choice because we don't care about little things. We just want to get the bulk right, and we don't have little pixels to worry about. So as a rule of thumb, right? But usually what happens is that you can try out for your problem which one is giving you better results. But as a rule of thumb, when you really care about small objects, then go for the DICE score, right? Okay, so we'll go over the code, but here just to give you an idea, right? To give you an overview how this thing will progress. We already talked about the model backbone. When we write the code, we will make sure that even though we are using the DeepLab v3 architecture, we need to choose whether we want to train a ResNet 50 architecture, right? A ResNet 50 backbone, or a MobileNet v3 backbone. And that will basically depend on where you're going to run this model, right? If you're going to run it on a small device, then you can train it on MobileNet v3, right? It will be fast, not as accurate, right? But if you want more accuracy, then you would use ResNet 50. There is another one, ResNet 101 is probably also in this option, but hopefully you don't need to use that. Then the image size that we are going to use is 384 by 384 by 3 is for the RGB pixels. Now you may be thinking that why is it 384? Why not 256? Why not 512? This is what the original authors trained it on, okay? The mask has a shape of 384 by 384 by 2, right? Now you may be thinking that why do we need two masks? One is sufficient, and that is true. But this model has been developed for general purpose segmentation, right? So when you use DeepLab v3, in our case, we have a simpler problem. We just need a binary mask, right? But it is the architecture allows you to do any kind of any number of masks, right? So you could have let's say you could have three masks, right? One for apples, one for oranges, and one for background. Let's say you were in a fruit situation, right? So basically, the same architecture can be used, can be extended to multiple objects, right? Multiple masks. But in our case, we just have two masks, background and foreground. Uh, so that's the number of output channels will be 2, right? And again, this is because how the architecture is already proposed. It is for multiple channels. We are using 2 channels. Number of epochs is the number of times the training process has gone through the entire process, the entire data set. So let's say you have a data set of 1,000 images. You don't actually train on all the 1,000 images in one shot. You actually take a smaller subset of that image, randomly select a smaller subset of those images, and that is called a batch size, right? Or mini batch size. In this case, we are setting it to 64. So out of the 1,000 images, we would select 64 images and we will train the model. Then we will and update the weights, how accurate it is. We will look at the loss and see how accurate is the model and then update the weights. Then we'll randomly select another 64 images and go through it and so on and so forth. Once we have traveled through the entire data set, right, 64 at a time, we have gone through the entire data set. That is called an epoch, right? And here we are saying, here we are saying that we are going to go over the training data, the entire training data 50 times. And basically the number of times you go depends on whether your accuracy is decreasing or not, right? And for this problem, we saw that, okay, 50 is enough. But let's say your accuracy is still improving or your loss is decreasing, then you can keep going for a longer epoch and you will get better results, right? Then there is something called optimizer. So there are 3 things here, right? One is the input image and the mask. And then we have these weights that need to get updated. And finally, we have the output. The difference, the loss, the difference between the input and the output, the error we are making, that is captured using something called a loss function, right? The loss function is high. The loss is high when we are making a lot of mistakes, and the loss is low when we are making less mistakes. So based on the loss, we need to go and update the weights, okay? Now, there is a mechanism. How do we update the weights based on the loss? That is governed by something called an optimizer, right? And I'm not going to go over the optimizers, but Adam is a very common optimizer. It is adaptive moment-based optimizer. In our courses, we explain all these things in great detail, but I cannot go over them here. But there is an optimizer involved. There is a piece of code, right, that governs how to take this loss function and update the weights, okay? Then,
if you want a deeper dive, you can go to opencv.org/university.
Exactly. Right. Then we have something called a learning rate. Learning rate basically says how fast do you want to learn, right? So imagine that you are, the error surface is like a bowl, right? It is like a bowl. You are on the top of the error surface. Think about your position, your loss as a marble, which is a spherical object that is going to go down, right? And you have this bowl. If you go down very fast, right, then you are training very fast, right? Your error is going down very fast. But you will also overshoot. There's a good chance that you will overshoot and miss the bottom and be thrown away, right? You will land in a different place. So you may want to go fast initially, but as you approach the bottom of the surface, you want to go slower, right? The learning rate controls how you go, how fast you go. So when you start the training process, usually the learning rate is high, and then gradually over time you slow it down as you get closer to the bottom of the error surface. So that's learning rate. Loss function I already explained. Loss function captures what kind of error you're making, and this loss function is used. The loss that is calculated over all images, it is used to update the weights. Okay. And then we have the evaluation metric that we just discussed, right? So loss and evaluation metrics, they are closely related, right? But the evaluation metric, we usually run on the test set, on the validation set, to see how accurate our results are, right? And loss, basically, it is a function of what mistakes that we are making so that we can improve the training error, right? So loss, we check the loss on both the training set and the validation set, but usually the loss on the training is the only thing that is used to go and update the weights, okay? And then, okay, so then finally we have shown some results here, okay? Just to give you an idea, these are the results we will expect. We will start with an image. If you use traditional, these images, if you use a traditional computer vision technique that we described before, you will get outputs like this, right? But if you use MobileNet v3 or ResNet 50, you will get more reasonable results, right? And this is the only part of the pipeline we are going to change in this. So basically, this tutorial is a tutorial on segmentation, all right? Now let's go over the code. I'm hoping that you have an overview. It's not easy to keep everything in mind, but bear with me. We'll go over the code and maybe this becomes easier. Okay, so even on the code, let me start with the bottom of the code first, and then we will start going to the top, right? Right, so okay, so this is the part of the code where we'll begin, and then I'll go to the top of the code and see how data is loaded, etc. So here we are setting up the code for training, right? The number of epochs, as I said, it is the number of times we are going over the training set. Here we have, in this notebook, we have set it to 2, but you will need 2 epochs is not going to produce a good result at all. You'll have to go to about 50 epochs, okay? Batch size, we set it here. Number of classes, here there are 2 classes, the background class and the document class. But let's say you had a more sophisticated segmentation problem, then you would have many more masks. And the number of classes also it will define how many masks are created in the end. So if you have 3 classes, then it would create 3 different masks, and you can use that mask to segment out that particular class, right? Device, it's basically the GPU or the CPU that you want to work on. Make sure for this particular notebook, you are using a GPU, otherwise it's going to take you a long time. I think on this GPU, it takes about 3 hours. If you use 50 epochs, it's going to take you 3 hours or so. Then we have the background model name. As I had said, that there are 3 options. One is a MobileNet v3, and this is, you just need to know this is what it is called by the model. So MBV3 basically is MobileNet v3. R50 is ResNet 50. R101 is ResNet 101. So ResNet 50 is the workhorse in many, many different applications. So you will often see ResNet 50 come up, right? And this was, I cannot even remember, it's an old model, but it has proved to be very, very useful, very, very robust in many different applications, okay? Next, we need to prepare a model, and we'll go over the code for preparing the model. It basically says, okay, this is the backbone we are going to use, right? And the number of classes, right? So that's simple. And then we are going to load this model onto the device of our choice. In this case, I think you should use a GPU, otherwise it will take you a long time. Then we can pass some dummy data into it just to see how this thing works, right? Now let me go. After that, we have this. We'll go over all of this data, all of this code in a little bit, but let me show at a high level what we are trying to do, right? So we are going to get the data, right? We'll first create the data set, and the data set will take in, what is the directory that we want to go. And then it will also require the batch size, because when we ask the data loader to load the data, it will load the batch size number of images at the same time. And then we have something called a device loader, which loads this data onto the device, right? And we are doing this for both the training data and the validation data. Again, we are not loading the entire data set. We are loading 64 images at a time, right? So that is something to keep in mind. Now, we are also saying that the evaluation metric that we are going to use is intersection over union. And remember that we had two options. We could use the DICE score, or we could use the IOU. And we decided that, okay, we are going to use IOU because, for this application, it may be right. But try out the DICE score. It's not going to hurt for this application. But let's say you had a biology application with small objects, then the DICE score would be better. Okay. So then we need to create a metric function, right? The metric function basically takes in the number of classes, which in our case is 2. We tell it whether to use the DICE score or not. And then, we have to load this to the device as well. Then we have to specify the loss function. Again, the loss function is very simple. We again say what kind of DICE function we want, what kind of function we want to use, whether or not to use DICE, and then we load it into the device. And finally, we have the optimizer. And if you don't know anything about optimizer, just use Adam. 95%, maybe 90% of the time, Adam is just going to work out of the box for your application, right? So the optimizer, it needs all the model parameters, and it also needs to know how fast you're going to train your model, right? The learning rate. There are other things called learning rate, schedule, etc., which, or sometimes it is also called cooling schedule, where the learning rate basically is slowed down over time. And sometimes if you're, one of the things that I remember the learning rate very clearly, because this is the first mistake I made when I was training a model, maybe a decade back. My first deep learning model, my learning rate was very high. And even though I changed it by a factor of 2, I thought that, okay, my the training error was just bouncing around. It was all over the place. And I thought that it is the learning rate is high initially, I thought. So I decreased it by half, and it still didn't do anything. So I just stopped fiddling with it. And I showed it to my friend who had done deep learning quite a bit for a couple of years back then. He just looked at my graph and said, oh, your learning rate is too high, right? And he changed it by a factor of 10, not by 2. So I changed it by a factor of 10, and then everything was working perfectly, but I spent like 2 hours because my learning rate was off and things were not converging, right? So that's my little story about learning rate. Okay, so you set up the optimizer, and then then you basically go over the data one epoch at a time, and then you plot the results, right? And here there are just 2 epochs, so you don't see the results. Ideally, what you would see is this training error. So this is the error plot. This would come down. It would be like a graph. You could think about it like a logarithmically decreasing graph, and then it will settle down at some value over time, right? If you get those kinds of graphs, then it's great. And then the validation error would be usually higher than the training error, right? It would be slightly higher than the training error because training data, the model is being trained on the training data. It has already seen it. It will also memorize some of the training data, right? In some cases, validation data is completely new. It has never seen it. So validation error would be usually higher than the training error. And similarly, the opposite would happen with accuracy. Just because you get very good training accuracy doesn't mean that the model has generalized. You will have to make sure that it is, you'll have to make sure that it works well on validation data. That is the accuracy you have to report, because that's the data it has not seen. The training accuracy could go to 100 if you on classification problems, if you train longer or if you use a very big model. then it will memorize everything, and the training data can go to 100%. Training accuracy could go to 100%, but then you see the validation accuracy, and if it is low, it means that the model is still not good, right? It may look very good on the training data, but it's not good because it has overfit the training data. Okay. So now let's go over the different pieces one by one from the very start. Okay. So here in this notebook, which Vikas will share if he has not already shared in the chat section, we want to make sure that our NVIDIA SMI, this is the command that shows you what are the devices available, NVIDIA devices, GPUs available, and you can see it's a useful command for people who are beginners and may not know. Then we install some plotting tools, and we install this torch metrics. Basically, it helps us create the IOU and the other metric, the dice score, etc. And then we also have the data for you. We have already created the data set and put it in this zip file, which is downloaded here, and then we unzip the zip file. We also download the model, right? Because these models, especially the MobileNet V3 model, that's we give you a path to download it. wget, for people who don't know, it's just a command to download a link through command line, and -o basically sets to a particular file, right? So it will download this link and set it to this file, save it on this file, right? And then we have the document scanner app, which you can also download. It will be located at this thing. And once everything is downloaded, we simply remove after unzipping the files. Okay. Then we start with a bunch of imports. All the important utilities and libraries, etc., are imported. People who may not know, this is used for creating a progress bar. Torch Vision is a very important library which has all the models. So all the model architectures and the defaults, what is the mean and median of those architectures, etc., we know through Torch Vision. So if you're using PyTorch, Torch Vision is, you will use it all the time. Another important one, these two are important classes, dataset and data loader. And a lot of times people think that, okay, they should be writing their own data loaders, but you should not. As much as possible, you use what the framework provides. That is because they have very efficient ways under the hood. They have very efficient ways to load the data, to batch it. All these things, they do it much more efficiently than what you would do yourself. So use the framework as much as possible, right? So we have the data loader and the data set, and we'll extend some of these in a class. This package called album, you read it as album and then entation, right? Albumentation, that provides you augmentation routines, right? It helps you create more data from your existing data through data augmentation, right? And then this is for plotting your loss functions, metrics, and some standard ones, right? We are saying that we are going to import these DeepLab V3 MobileNet model. We are going to use DeepLab V3 ResNet, and we're also going to import ResNet 101. And depending on which one we choose, we will train our model, okay? Before we do anything, we need to set the seeds so that your experiments are reproducible, right? So these are basically random number seed generators, and there are several places that you need to set this seed. If you don't do this, every time you run the experiment, you'll get a slightly different result, and then you won't be able to reproduce your experiment. So it's very important to set the seed. Usually we set the seed to 42. If you don't know this, you should know it. It is just an insider joke.
The answer to life, the universe, and everything.
Exactly. We don't know the question though, right? So
That's
then,
right.
we set some. Our data set is already resized and it is in this folder. We say this is the model. This is a pre-trained model, right? That already exists. We are going to fine tune this model, which means that we are going to change. We'll start with a model that has been trained on millions of images, and we'll fine tune it for our own application. And then the image size and the number of workers are defined here. Number of workers basically means, when you're loading your data, how many sub-processes are used to load that data. That is defined by the number of workers. You may be thinking, why don't we make it 100 and it will be really fast? The thing is that you may overload your system if you're using a lot of workers. So, 2, 3, 4, that's a good number. Next, whenever we load the data for training, we have to transform it, right? So when the original MobileNet or original, data set was loaded, usually we remove the mean and divide the mean subtracted part by the standard deviation. So let's say you have an image, right? An image goes from 0 to 255. First, you divide the entire image by 255. So it goes from 0 to 1 now. Its floating point, it goes from 0 to 1. Oops, okay. And then there are 3 channels, right? So we subtract from each channel, we subtract the mean. So this is RGB. We subtract the mean of from this image, and then we divide this value, the mean subtracted value, by the standard deviation. And this is a standard normalization that is done on the image. Now you may be thinking, where does this mean come from? Most likely this comes from, I'll have to check, but most likely it comes from the COCO data set on which the originals were trained, right? The original model was trained. It is the mean of all images in that data set, or they might have sampled it. And this is the standard deviation of all images, right, in the data set. So the very first thing you do is you subtract out the mean and divide by the standard deviation. And this is what is being done here. You can also do a few tricks, right? You want to make sure that this is, if all the images in your data set are color images, you want to make sure that it also works on grayscale images, right? So randomly with probability 0.4, we change some of the images to grayscale, right? And in our application, that is a fine thing to do, so that we don't explicitly collect grayscale images. We just change them as we load them, right? So those are the transforms that are applied to anything we load, right, for training purposes. There could be other common transforms which is not used during the training process, but let's say during inference, we don't need to do this we don't want to change it to grayscale, right? We don't want to change our image that we want to run the model on. In that case, the only thing that we need to do is remove the mean and then divide it by standard deviation. So this transform is used when we want to do inference. Next, we want to create the segmentation data set, right? Oops. Okay, here. So the segmentation data set, it extends the data set class, right? And here we need to give it a type, and the type, there are 2 types, train and valid. Valid is for validation. And then we need to give it the image paths. We need to give it the path for the masks, and then the image size, right? And all these things are set up. And then when we are doing training, we want to make sure that the training transforms are applied. Why does it keep moving? Okay. So when we are doing training, we want to make sure that the training transforms are applied. And when we are doing inference, that means we have a trained model and we are using it. Then we just don't care about the grayscale, converting it to grayscale. Okay. Next, there's some code to read the image file, and some of you may see this code. We want to make sure that once the image is loaded, OpenCV loads these things in a BGR format, and this piece right here, it changes it to RGB, right? It permutes it to an RGB image so that NumPy and everything, when we display the image, doesn't look funny. And also because the mean, when we subtract the mean and divide by standard deviation, the right channel mean is being subtracted. All right. And then this dataset class, right? It also needs some standard functions like get item, which gets one single item from the dataset, right? And here there is just, I'm not going to go over this code. It is pretty much self-explanatory. When we say item, it gets the image and it gets the mask for that image. All right. So next we learn the data set, right? We load the data set. We get the training image, right? We get the training image directory. This is the directory. This is the mask directory. Again, the validation image directory, validation mask directory. And then we get all the paths, right? The data set, all the paths, all the images in that data set we get those for both training set and validation set. And then we finally create the data set, which takes in the image paths, the mask paths, and then we say it is train type train. And then this is of type validation, right? And then we have, then we declare a loader. The data loader, right? It needs the data set. The data set is the set of all images, right? But the data loader helps from this set. It helps us batch. For example, here you can see we need to provide the batch size. So from these 1,000 images, whatever our data set is, it could be 1 million. Think about it, right? We don't want to load all 1 million images at the same time. So we have defined our data set, but then we need to define a loader, which will basically take this, get us the right number of images. And here the batch size is 64 at a time. We are going to say use 2 workers. Let's say you have, you have a beefy machine. You can go, 5, 6 workers, and it should be fine, right? So we now have the data loaders, and the data loaders are like iterators, right? You can go and iterate over, and it will get you, a batch of 64 every time. Okay, so now we do the get data set, and we load our, train loader and data loader, and it just gives us this data, basically it loads the, we get the loader from this get data set function that we had defined earlier. If you look at what the data loader, a single output looks like, you will see that, we have a tensor which has this kind of thing, right? A single image is represented using the one, here represents one image, right? You could have multiple images in the batch, but here we have one image. This is the RGB 3 is for 3 channels, and this is the width and height. And that's the input. The output is 2 masks, one for the background and one for the foreground or the document. And then we have the same size, okay? One other thing I maybe did not mention in this, when you change an image to tensor, it basically means that from a RGB, it's a 3-channel image, and then there's the width and height. But when you change it to a tensor, it adds one more dimension to the data structure, because that one dimension is for the batch size, right? So that is why when we change the image to a tensor, we start getting these kinds of tensors, right? It is in this format. It is no longer width, height, and the number of channels. It is batches, number of channels, width, and height. Once we get the results, right, we also need to denormalize the image, and it is basically the inverse of the normalization process. So denormalization is nothing but we multiply by the standard deviation, as you can see here, and then add the mean to every channel. And then we want to, sometimes because of numerical imprecision, things may go below 0 slightly or above 1 slightly. And we just want to clip those. And that is what is happening here. Okay. This is simply some plotting function, right? And I'm not going to go over that. You can go over that. But once you plot this image, you will see these are the kinds of images we have. We have the image. This is what the background mask looks like. And it is basically the inverse of the document mask. Okay. Now, as we had said, let's look at what prepare model does, right? In our code below, we have something called prepare model. We define the backbone, which is one of these three, right? And then there's one more important thing we need to do. This model, right? This was trained on COCO dataset, which has 1,000 classes. But in our case, actually, it may have more classes. I'm blanking on it. ImageNet has 1,000 classes, but the COCO dataset has a large number of classes, right? But our dataset has only 2 classes, right? So we have to modify this architecture, which had an output of, let's say, 1,000 classes. Now we want to modify it so that the output has only 2 classes, right? And the way to do it is we do this model.classifier. This is the end classifier. We say that we want to change it. We want to replace it with 2 classes, right? Here, num classes is 2 in our case. And there's another thing called auxiliary classifier. Let me show you. Yeah, this. Okay, so in DeepLab v3, if you, this is what it roughly looks like, right? So sometimes what happens is when you use a model architecture, it could have many different layers. It could have many different, it can be very deep, right? That is the part of deep neural network. But as the models get very deep, they have many, many different layers. In those cases, the gradients they become vanishing, they become very tiny, which means that the signal, right? The signal that is actually used to modify the weights, that is getting smaller and smaller and smaller as you have, deeper and deeper networks, right? And so, sometimes that is why it was very difficult to train very deep neural networks before. But now there are many different mechanisms to solve that problem. One of the mechanisms is to use something called an auxiliary classifier, right? So you can imagine, we know that, the end classifier, which is at this level, right? The end classifier produces 2 masks, right? The background mask and the document mask. And it is a very fine mask, right? It is, every pixel has a label to it. So for every pixel, we have either it is white or black, right? But in this stage, at this stage, we can actually extract a mask even at this stage, which, because if you look at this carefully, we just have repetitions of the same structure, right? So the more deep a neural network is, it means that it can learn a lot more, right? But if you actually try to get a mask from not so deep layer, you can still get a mask. It will not be very accurate, right? But this mask has enough information to drive the training process. So the accuracy, when we are trying to build a loss function, right? The loss is dependent on not just this loss at the end of this deep structure, but also at intermediate levels, right? This auxiliary classifier, they provide some information. And because they are at not so deep level, they help us avoid that vanishing gradient problem, right? It amplifies the signal, because if the mask is going to be good at this level, at the end of this model, it also needs to be relatively good at this level, right? So you have a representation of the mask at not so deep level, which adds to the loss function, and it guides the loss function in the right direction. Hopefully that is roughly clear. Just the intuition of it, right? What do you think, Phil? Was that relatively okay?
I don't know if you could do better without spending, another half an hour on it.
All right, all right. So, okay, my point is that there is the final classifier, but there are also auxiliary classifiers which are in between, right? And because the classifiers also have, the number of classes would be based on the training set it was trained on, we need to fix the auxiliary classifiers number of classes also, right? And once you have done that, your model is ready, right? And then we are going to load the model. We are going to prepare the model. We are going to say that, okay, the number of classes is 2. And then we set it to the training mode. The model works in 2 different modes. One is the training mode, and the other is inference mode. The reason it is important to specify is that during training mode, in the training mode, it actually, when it's doing the passes, it is calculating the gradients, right? It is calculating the information which will be useful for updating the weights. But so it is more expensive. The training loop is much more expensive. But when it is just applying the model weights to a new image, in that case, it doesn't need to update the weights, right? It is using it for inference. And that is why, that's the difference between the 2 modes. So we have to set it on in training mode because we are interested in training. And then, just to get an idea what this would look like, we put an image, a random image in, and we want to see the shape, right? So we put the random image in, we ran this model, it downloaded the right model for us, and then it output something, we don't even care to check what it is, but at least the dimensions are right. It has 2 images, and then it's a 2-channel mask, one for the background and one for the foreground, and it has this dimension. So we are able to verify that the modification that we had made to the model, that it should produce a 2-channel image, it's working, okay? And here we basically, we do the calculation for the loss and the metric, right? We calculate the intersection, we calculate the summation, and when we use dice score, in that case, the formula is 2 times intersection divided by the summation, the sum of the 2. And in case of union, we have to, the summation contains the intersection also, right? So we have to subtract the intersection, and then the metric, IOU metric, becomes intersection over union, all right? And then, this metric is calculated on a per pixel basis, right? And we want to make sure that we report the results on all the images, the mean results on all the images and all the pixels. And that is why we are setting this thing to mean. We are interested in a single value, which is the average, right? We are not interested in a mask. We are interested in a single value. So the total is basically we calculate the mean and send out the total. Okay. Similarly, the loss is basically when we calculate the loss, we have the prediction and we have the target. The target is the ground truth. The prediction, we want to make sure that the prediction is a probability between 0 and 1. So whatever prediction we had, we are converting it to a probability using sigmoid, right? Sigmoid, whenever you want to take any number, let's say your values change from 0 to some very large number, and you want to compress them to probabilities, then an easy way is to use the sigmoid function to do it, right? The values would land between 0 and 1, but using an S-curve. You could say that, why don't we just divide it by the maximum? Because the maximum may be an outlier. It could be a very, very large number. And the sigmoid has that, S-shaped curve, which makes it almost like a step function, but not quite. So I think I'm running out of time, but okay.
Getting
So
close.
the loss that we want to use is called the binary cross entropy loss. Without going into the detail, basically it takes the prediction and the target, and it creates, when you create this cross entropy loss, it gives you a value which is low when the prediction and target values are the same, right? And it gives you a high value when these are high. Then we also need to supply a reduction. Now, these predictions are made on a per pixel basis. We want to aggregate the prediction, right? And how do you aggregate? You could, how do you pool this information? And that is done using this field called reduction, right? You reduce using mean, so which means that you take the average of all the values, right? And then the mask loss, as I said that, the metric which we are using, it is the opposite of the loss, right? So this metric that we are using, it is high when the metric, the intersection over union, it's high when it is desirable and low when it is not desirable. Loss, on the other hand, is the opposite of it. The loss is high loss is undesirable, right? And low loss is desirable. And that is why we are subtracting it from 1, right? So that it inverts. And finally, basically, there are 2 kinds of losses. One is the pixel loss that I mentioned, the cross entropy loss. And the other one is the loss based on the mask, how much the masks are overlapping. Both those things are contributing to the final loss, right? And once we get this final loss, we can basically use this loss function to train our model. Okay. Again, so here this function convert to one shot. Now, when you have a 3-class, let's say our model right now, we just have a binary classification problem, right? So it is 0 and 1. But let's say we had a 3-class classification problem, right? So we had 3 classes, and let me give you an example, right? So you could say that, okay, if you do a simple encoding, there are 3 classes here, right? Elephant, table, etc. If you do a simple encoding, you could encode it using 0, 1, 2, 3, 4, etc. Right? The problem with this kind of encoding is that it feels, because these are numbers now, it feels that a table is closer to an elephant in using, because 1 is closer to 0, 2 is closer to right, and this helmet is far away from the elephant, right? So if we encode it naively using this kind of thing, we run into this problem. Intrinsically, it is thinking that table is closer to an elephant than a tomato, right? Which is not true, right? So one-hot encoding is basically
it's a deep philosophical question.
Right. So in one-hot encoding, we basically take this, the number of classes, we create a vector which is the same as the number of classes, and we put 1 for the first class, and 1 here for the second class, 1 here for the third class, and so on and so forth. Now, you can know, if you look at this vector, right, and this vector, they are equidistant. Think about, think about 3 dimensions and then, expand it to 5 dimensions in your mind, however you want to do it. But they are equidistant. You can see that the distance between this and this is √2, right? Or √2. If you want to do 1 minus 0 squared, 1 minus 0 squared, and everything else is 0, and you take the square root. This one, the distance between these 2 vectors is √2. The difference between these 2 vectors is √2, and so on and so forth. So now all of these notions are equidistant, and that is why we use one-hot encoding, right? And this piece of code, you can go over it. It helps you create a one hot encoding for the number of classes you have. So moving on. And then we have this metric class, right, which basically we want to make sure that, we are getting during forward pass, when we are training the model, right, it is creating a prediction. It is first doing a one hot encoding of our classes, and we get the prediction vector, and then we calculate we calculate the metric from this, right? Either it is a dice score or the intersection over union, right? We calculate it and we return it. The metric class simply returns the metric which we already went over. So one thing some people may think, what is the smooth? Smooth is basically, you can think about it as, it is added when you're calculating the dice score, the numerator can actually be 0. So the smooth, it's a small number that is added to the denominator, as well as the numerator. The small number is added on both numerator and denominator, so that you don't get a divide by 0 kind of situation. All right. All right, we are coming close. Let's see what else is left. As I mentioned, to-device basically sends all the data to the device or the GPU. And then we have the device loader. Don't have to worry about it. It basically loads all the information to the device. And the only thing left here is the step, right? So step is a function that basically takes that is one step in the training process. And one step basically takes an a batch size of data. And then it does a forward pass, right? And it looks at the loss. And the optimizer then goes and changes the weights based on the loss, right? So you can see that, here the data is loaded. When it is, when we are training, right, we want to make sure that, the gradients are calculated properly and everything is done. But when we are doing inference, we want to make sure that no gradient is calculated. This is just, otherwise you will spend a lot of time during inference when you don't need to calculate the gradients. Gradients are calculated to update the weights or train the model, right? You get the loss by passing, the predictions through this. So the predictions, we get the predictions by running the data through the model, right? We get the predictions, and the prediction is used to calculate the loss function because we know the ground truth. So we get what the loss is. And if it is in the training phase, then this loss needs to go and update the weights, right? So loss.backward basically does a back propagation, or backward. Back propagation is the algorithm that is used to propagate the loss. When the loss is high, we need to update the weight in a certain way, right? So it is basically telling the model to update the weights using this algorithm called back propagation. And then finally, we need the optimizer. The loss function informs, how the optimizer informs how this loss function will be utilized to update the weights. And so the model basically updates its weight in this piece of code, right? Then we calculate the metric, right? And we calculate the loss value, and basically we report what is the current loss and what is the current metric. And this basically is returned, right? And we already went over the training process, right? And, if you run it for 50 epochs, you'll be able to train your own function. And these graphs, they will start looking like, L-shaped. Ideally, the loss function would look like an L-shaped thing. And this one should look like an inverted L-shaped curve. Yes, that's pretty much it. And once you run this, the rest of the code remains the same. This extract code here, this basically is similar to the one that we discussed in our last webinar. And this will keep going, right? It's pretty much the same code. And once you are done with this, you will see results like this. Given an image like this, it will produce an image like that. And here we are assuming that the original, the aspect ratio of the original image is the aspect ratio of the document, right? So given this document, it will create the same aspect ratio, and you will see this image gets modified to this image gets modified to this, and so on and so forth, right? So pretty reasonable results, because these are pretty arbitrary images, right? So let's do the questions real quick, and then sorry, we ran out of time. I have a hard stop at 10:30. So sorry about that.
Let's do our giveaway here.
Okay.
So yeah, you can go ahead and unshare your screen there, Doc. Hey there, everybody. Thanks for joining us here and sticking around. We went a little bit over today, but this was I learned something in this episode. I hope you did too out there. Lots of good feedback from all of our stuff. In case you need a little reminder, or if this is your first time joining us, one of the things we do on every single episode of OpenCV Live is give away something to you in the audience. I'm going to give away the OpenCV course of the winner's choosing of our trivia question here on OpenCV Live. The way this works is I'm going to ask a trivia question that I made up during the presentation from Satya, and the very first person to answer that trivia question correctly in the Zoom chat will win the OpenCV course of their choosing. You can go to opencv.org/university to see what courses are available. If you have won in the last couple of months, please do not answer and give someone else a chance to win a course. This one is going to be a rare three-parter here. We talked about primarily, we talked about using three different neural networks here in our product. What were the names of those three neural networks, folks? What were the names of the three neural networks that we talked about using during the project here today? There were three of them. Two of them were named pretty similarly, but not exactly the same. Not exactly the same. Some of you have some of them. You have to name all three. The person that names all three
just to
in
clarify,
one
it's the
message.
backbones. Yeah.
Yes, exactly. All right. It looks like we got one here. No, close. You're off by one. You're off by one. Oh, you got one. Okay. I think we have to. I think we're gonna call it. Some of you got really close, but you fat fingered the thing. We're not gonna. It doesn't have to be perfect. I think the first one that got it pretty much right was Venkatesh. Here I see ResNet 50, ResNet 101, and MobileNet. That was the answer we were looking for. Yeah. That was the answer we were looking for. Congratulations, Venkatesh. Please send Venkatesh Kumar. Please send one email to phil@opencv.org with the course you would like. Once again, please go look at opencv.org/university to pick a course, and then send me an email with the course you want. Congratulations. I guess let's see. We've got you gotta leave, Doc. Next week we are lucky to have Kimberly McGuire from BitCraze, makers of the awesome Crazy Fly these awesome little tiny drones that you can collaborate with. Very cool. We're going to be talking about the importance of demo-driven design mentality with robotics and drones. It's going to be a real treat. And then the week after that, we've got Max Van Leeuwen, and the week after that, we've got the future of robotics regulations. We are booked solid, folks. We love to see it. Doc, you want to take us home?
Yeah, thank you so much. It's kind of tough to go over notebooks over a short period of time. I hope that not everything would have been 100% clear, but if you took away a few things from this tutorial, that's enough, right? A few good ideas are enough to learn in 1 hour 20-minute session. I hope it provided good some learning to some of the folks at least. And if you want us to do more of these, please let us know in the feedback form, and we will do more of these. When we get feedback on these things, we know that this is what people like, and we do more of these. All right. And I want to thank everybody. Right. Yeah. Thank you, Phil. Thank you, Vikas, for supporting us.
Thank you, everyone.
Yep. Yeah, thanks for joining us, Vikas. Thanks so much for watching the show this week and every week, everybody out there. We actually set, this is our most watched episode in like 3 months. So thanks a lot, everybody. Right. We'll see you next time. Take care of yourselves out there. Take care of somebody else if you can, and have a great day wherever you may be.
All right. Thanks. Bye.